We'll start in 1 minute. Today we'll start section 8.3. The first part is on hydrostatic pressure and force. We begin with some definitions on hydrostatic pressure and force. Suppose a flat horizontal plate with area capital A is under a liquid at depth D. Then the volume of liquid above the plate is capital V equals the area times the depth. And so the units for the volume are cubic units. We're going to let rho, the Greek letter rho, represent the density of the liquid. And G represents the gravitational acceleration. Okay, so the force of the liquid on the plate is rho times G times A times D. So A times D is just the volume. Rho times the volume is the mass, and G is the gravitational acceleration. So you might remember that force is mass times acceleration. The pressure of the plate, capital P, is equal to the force divided by the area. So that's rho times G times D. And this is just the force per unit area for the pressure. In the international system, the mass density of water, represented by rho, is 1,000 kilograms per cubic meter. In the international system, the gravitational acceleration is 9.8 meters per second per second. That's the rate of change of the velocity. And the volume of a column of water is the area of the base multiplied by the depth, so A times D. And a unit of force is 1 Newton. 1 Newton is 1 kilogram meter per second per second. And then 1 unit of pressure is called a Pascal. 1 Pascal is 1 Newton per square meter. And a kilopascal is just 1,000 pascals. In the US customary system, the weight density of water is rho times G, and that is 62.5 pounds per cubic foot. Okay, the force is rho times G times A times D, But in the US customary system, force is measured in pounds. And the pressure, same as above, of course, pressure is force divided by area. And in the US customary system, the pressure is measured in pounds per square foot. Okay, the next page. The principle of fluid pressure is that at any point in a liquid, the pressure is the same in all directions. And now suppose a vertically oriented plate is submerged in a liquid. If the plate is vertical, then knowing the area of the plate isn't enough to determine the hydrostatic force on one side of the plate, because the hydrostatic force increases as the depth increases. So below, we'll describe how to find the hydrostatic force that's exerted on one side of a vertically oriented plate that is submerged in water. Well, think of the XY coordinate system rotated 90 degrees clockwise. So if we do that, then the positive y-axis will be horizontally to the right, and the positive x-axis will be vertically downward. So the reason I think that this is done is we can describe the depth in terms of positive x values if we start at the top where the surface of the water is and move downward, the x values increase in the positive direction, corresponding to the depth increasing. So up here at the top, this is the water surface. And we're going to suppose that we have some vertical plate of an arbitrary shape. And we want to see if we can come up with an expression for the hydrostatic force that's exerted on one side of this vertically oriented plate submerged in water. Okay, well, on the positive x-axis, the tip of the top point of the plate, let's refer to that as x value A, and the bottom x value B. And we're going to subdivide the interval from A to B into n subintervals, each of length delta x. So as usual, delta x is b minus a divided by n. And we'll single out one of those subintervals from x sub I minus 1 to x sub I. And so delta x is equal to the length of that subinterval. So in particular, delta x is x sub I minus x sub I minus 1. Okay, then we're going to construct a rectangle that approximates the area of that portion of the plate. So the vertical dimension of that is delta x, because it's on that interval from x sub I minus 1 to x sub I. And for an arbitrary x value on that interval, which represents the depth, we'll refer to that as x sub I star. So that's the depth. And then the length of the horizontal side of this rectangle, we will refer to that as the function w of x, but evaluated at x sub I star. So x sub I star, w of x sub I star represents the width, or the horizontal length of that rectangle. The vertical length is delta x. Okay, remember the hydrostatic force is the density rho times the gravitational acceleration times the area times the depth. Okay, so for really skinny rectangles, which is what you get if you allow n to be an extremely large number, the hydrostatic force on that rectangle is approximately the same as if the rectangle were horizontal instead of vertical. So the hydrostatic force on this ith rectangle, I'll refer to the hydrostatic force as F sub I. It's approximately equal to rho times g. Rho times g is always the same. The area of this rectangle is w of x sub I star times delta x. And the depth is x sub I star. So just as a reminder, A is the area of the rectangle. So this right here is what A is, and D represents the depth of the rectangle at a particular point. So x sub I star is the depth. Hey, well, we'll rearrange the factors a little bit, but the overall force, the overall hydrostatic force on the plate, if we get one of these expressions for each of the n subintervals, then the hydrostatic force on the entire plate is approximately equal to a Riemann sum from I equals 1 to n of rho times g times w times x sub I star times x sub I star times delta x. Okay, this is a Riemann sum, so the force itself the exact value of the force is the limit as n approaches infinity of the Riemann sum. And then when we compute the limit, we get a definite integral. So the hydrostatic force is the definite integral from A to B of rho times G times W of X times dx. Okay, so that's it. This is the hydrostatic force. On one side of the submerged plate. If X is measured in feet, then the hydrostatic force is measured in pounds. But if X is measured in meters, then the hydrostatic force is measured in newtons. Hey, let's look at a few examples. Hey, the first one, a vertically oriented rectangular plate with dimensions 3 meters by 4 meters is submerged in water where the short sides are horizontal and the top side is 1 meter below the surface. Find the hydrostatic force against one side of the plate. So at the top we have the surface of the water. And a vertically oriented rectangular plate, the short sides are horizontal and the top side is 1 meter from the top. So this side is 3 meters, and the long sides are 4 meters. And so the depth of the plate ranges from 1 meter below the surface to 5 meters below the surface. Okay, so let's remind ourselves hydrostatic force is rho times G times the area of a rectangle times the depth. Okay, I'll pick out a rectangle as a reference. This is so just think of what we did on the previous page. Subdivide the interval from 1 to 5 into n subintervals of length delta x. And then we're going to find the area of these rectangles. So the depth, we'll refer to that as x sub I star again. And W of x sub I star. So you can probably just write down the integral, but let's do it in a couple of steps. The hydrostatic force on this particular rectangle is approximately equal to rho times g. The area of the rectangle is, in symbols, is W of x sub I star times delta x, and the depth is x sub I star. Okay, but W of x sub I star is always equal to 3 because it's a rectangle. The horizontal side is 3. So we can write this as rho times g times 3 times x sub I star times delta x. Just for practice, let's write down the Riemann sum. We get one of those terms for each of the n rectangles. So the entire hydrostatic force on one side of the rectangular plate is approximately equal to the Riemann sum from I equals 1 to n rho times g times 3 times x sub I star times delta x. And then when we let n go to infinity, we'll get a definite integral where x ranges from 1 to 5. In this case, since x is measured in meters, rho times g is how much? Well, the number is 1,000 times 9.8, so 9,800, and then times 3 x dx. So if you remember, the density of water is 1,000 kilograms per cubic meter, and the gravitational acceleration is 9.8 meters per second. 9.8 times 1,000 is 9,800. Okay, so let's take this a little further. So 9,800 times 3x to the second over 2 evaluated from 1 to 5. 9,800 divided by 2 is 4,900 times 3, and then 5 squared minus 1. So the units are newtons. Just a little more, 4,900. Let's see, 4,900 times 3 is 4,700, 114,700. And then times 24, whatever that is. That's the hydrostatic force measured in newtons. Yeah, that's a pretty straightforward example. Let's look at one that's a little more challenging. This one, a vertical isosceles triangular plate with a base of 4 feet and a height of 6 feet is submerged in water. The vertex opposite to the base is at the surface, and the base is horizontal. Find the hydrostatic force against one side of the plate. Hey, I have to draw a picture. So we have a isosceles triangle that one vertex is at the surface of the water. The base, 4 feet, is opposite that vertex. And the height or the altitude of that triangle is 6 feet. Okay, so we do know that the depth ranges from 0 feet to 6 feet. Okay, so we want, as before, subdivide the interval from 0 to 6 into n subintervals, each of length delta x. And then we'll want to construct rectangles that approximate areas. So I'll refer to this as the ith rectangle on the interval from x sub I minus 1 to x sub I. And so the depth will be x sub I star. And the vertical side of that rectangle is delta x. And we just have to come up with an expression for the length of the horizontal side of that rectangle. Okay, so once we have that, then it's not too hard to set up the definite integral. Okay, so let's look at half of that isosceles triangle, which is a right angle or right triangle. So this side will be 2 feet. The entire length is 6. And then let's suppose our x sub I star. So from there to there is x sub I star. And if we can find the length of this horizontal side of this small triangle, I'll refer to this as A. And then if we can find A in terms of x, then the length of the horizontal side of this rectangle will be 2 times A. So we can use similar triangles. The small triangle The horizontal side is A, the vertical side is x sub I star. So the ratio A divided by x sub I star, what does that equal to? Well, in the large right triangle, which is similar to the small one, the corresponding sides are 2 divided by 6. So you remember in geometry that if two figures are similar, then corresponding sides are proportional. So that's all we did was use similar triangles. And we want to know what A is. So multiply both sides by x sub I star, simplify 2 over 6. So we get 1/3 times x sub I star. And then our W of x sub I star, which represents the horizontal side of this rectangle, is 2 times A, or 2/3 times x sub I star. Hey, so we're pretty close. Let's just write down the approximation for the hydrostatic force on this rectangle. F sub I, the hydrostatic force on the ith rectangle. For now, we'll just write rho times g. And then the area, 2/3 times x sub I star times delta x, and then times the depth, which is x sub I star. And x sub I star times x sub I star is x sub I star squared, and then delta x. Okay, so let's go ahead and write the definite integral for the hydrostatic force. The x values or the depths range from 0 feet to 6 feet, so the limits of the integral are from 0 to 6. In the US customary system, rho times g is 62.5 pounds per cubic foot, so 62.5 is the rho times g. And then times 2/3 x squared dx. Okay, 2/3 times 62.5, let's write that as 125 over 3. And then an antiderivative of x squared is x to the 3rd over 3. And evaluate this from 0 to 6. Uh, 125 over 3. 6 to the 3rd is 216. So 216 divided by 3. And then minus 0. So if we divide 216 by 9, we get 24. So 216 divided by 3 times 3 is 24. So we get 125 times 24. So notice 125. This is just something you can do if you don't want to think too hard. 125 is 5 times 25. 24 is 4 times 6. And in the middle, 25 times 4 is 100. And then multiply 100 times 5 times 6, which is 30. 30 times 100 is 3,000. And the units in the US customary system are pounds. So 3,000 pounds is the hydrostatic force on that vertical plate. Okay, let's move on to the next example. Two ends of a water trough are semicircular plates, each with a radius of 2 feet. If the trough is filled with water, find the hydrostatic force exerted on each end of the trough. Okay, semicircular plate. Radius 2. So I still want the positive x-axis to be vertically downward, so x greater than 0. And the y-axis. Okay, along the x-axis between 0 and 2, we subdivide that interval from 0 to 2 into n subintervals. Guess I'll use green. And then we construct a rectangle to approximate the area. The depth of that rectangle will be x sub I star. The depth of the entire plate ranges from 0 to 2, so this will be x sub I star, representing the depth. The width of that rectangle is delta x, or the vertical side of that rectangle is delta x. And we would like to know what the length of the horizontal side is. Well, I think it's easier if we focus on finding half that length, because on the right side, that length is just y equals the square root of 4 minus x sub I star squared. The equation for the quarter circle on the right side is y equals the positive square root of 4 minus x squared. And I'll just point out a couple of things if it's not completely clear. So remember, the x-axis is vertical and the positive x-axis is vertically downward. So this equation gives us the y-coordinate that corresponds to an x-coordinate. So on the semicircle, when x is 0, the y-coordinate is 2, positive 2. And that works in this equation also. When x is 0, the y-coordinate is the square root of 4 minus 0, or 2. At the other extreme, when x is 2, what's the value of the y-coordinate? 0, right? When x is 2, the y-coordinate is 0. And that is true in this equation also. When x is 2, the y-coordinate is the square root of 4 minus 4, or 0. Okay, so all we have to do to find the entire length of this rectangle is multiply this by 2. So our hydrostatic force on the ith rectangle is approximately equal to rho times g times the area times the depth. Okay, the area of the rectangle, the complete rectangle, is 2 times the square root of 4 minus x sub I star squared times delta x, and then times the depth, x sub I star. You see that? Okay, once again, just to reinforce what we're doing. So this has the form rho times g times the area of a rectangle times the depth. So the depth is x sub I star. And the area of that rectangle is 2 times the square root of 4 minus x sub I star squared times delta x. Okay, so we can write the definite integral. Let's see, we're measuring, x is measured in feet, so rho times g will be 62.5 pounds per cubic foot. Since that's a constant, and we're multiplying by 2, we can write 125 times the definite integral from x equals 0 to 2. And then rearranging the terms, I'll write x times the square root of 4 minus x squared, and then dx. Okay, let's go ahead and evaluate this. So, any ideas on how to evaluate this integral, this definite integral? So, anybody online have a suggestion? Notice we have the square root of 4 minus x squared, and we also have a factor of x on the outside. So if we use the substitution rule, I got a reply. U substitution. If u is 4 minus x squared, then du is negative 2x dx. We see that we have x dx. So if I solve for x dx, I get negative 1/2 du equals x dx. Okay, so we'll bring the constant negative 1/2 out front and multiply it by 125. So we get negative 125 over 2. And then we change the limits of integration. When x is 0, the u value is 4. And the upper limit, when x is 2, the u value is 0. And then, instead of writing the square root of u, I'll write u to the 1/2, and then du. Well, we can proceed the way it is, or we can also fix it, if you want to call it that way. What do we do if we have a lower limit on a definite integral that is a bigger number than the upper limit? So an aside, if you have a definite integral from a to b of f of x dx, that's equal to the negative of the definite integral from b to a of f of x dx. So we can do that, or we don't have to do that. I'll go ahead and do it. So we're going to get the negative of negative 125 over 2, so positive 125 over 2, and then the integral from 0 to 4 of u to the 1/2 du. And then 125 over 2, an antiderivative of u to the 1/2, u to the 3/2 divided by 3/2. Dividing by 3/2 is equivalent to multiplying by 2/3. U to the 3/2 from 0 to 4. So we get 125 over 3, and then 4 to the 3/2 is 8. And 125 over 3 times 8 is 1,000 divided by 3, or 333 and 1/3. And the units are pounds for the hydrostatic force. Let's go ahead and get started on the next one, and we'll quit before it gets too late. This one, the length of each side of a vertical equilateral triangle is 2 meters. It is submerged in water with one side at the surface. Find the hydrostatic force against one side of the plate. Here we have a equilateral triangle. That means all 3 sides are the same length of 2 meters. So equilateral two meters. So we would like to know what the x values range from, we know that it starts at 0. So we can use a half of the equilateral triangle to find the height or the altitude of that. So if we just look at half, this side is 1 meter, the hypotenuse is 2 meters. And then the height, so use the Pythagorean theorem, we get h squared plus 1 squared equals 2 squared. So h is the square root of 3. Okay, then we pick a rectangle and find an expression for the area of that rectangle. Refer to the horizontal side as delta x. Okay, we're out of time. Go ahead and work on this and let me know if you have any questions. So go ahead and sign in for attendance.